zoom in and zoom out can't be like command plus minus, because that would make too much sense.
In which app?
Instead, it's like command shift period.
But which app? It does that in Chrome.
I'm talking about Apple apps.
Okay,
Yeah.
Apple apps, yeah.
I'm looking at notes specifically.
Okay. All right, about ready.
You're listening to Coding Blocks, episode 96. Subscribe to us and leave us a review on iTunes, Stitcher, and more using your favorite podcast app.
And you can go to codingblocks.net where you can find things like show notes and examples and discussion, whatnot.
Did you just say twice in that sentence?
That's right, man. Take it.
Oh.
Well, Alan, it's your turn. Alan.
Oh, that's it. I'm walking away.
Alan? Can we change his name from Alan to Alan?
Alan?
No.
Feedback, questions, and rants to comments at codingblocks.net. Follow us on Twitter at codingblocks or head to www.codingblocks.net and find all our social links there at the top of the page. With that, I am Alan Underwood.
I'm Joe Zach.
And I'm Michael Outlaw.
I just vomited. All right. So as we like to do, we like to start off each episode with a big thank you to all those who have taken the time to leave us a review or written us. So either which way. So on iTunes, we've got Crosseling, JLA 115, Ross44 Ross, Hutchibong, John Mabel, Code in My Robe, Maltashi. I'm going to go ahead and do him some justice here because he went through the effort. Sexton Edger, maybe, and then Bubba Cow.
All right, and Stitcher, we've got Jarvinen, sorry about that. Elelville Cole Israel, SB Good, Maxim Bendius, and Nathan Iyer. We really appreciate that. Thank you so much for leaving those reviews. Even though we butcher your names, we really do appreciate it. So thank you. You rock.
Wait, is that Iyer or Liar?
Oh, I don't know.
I
don't know. But
hey, by the way, I forget who it was, but whoever said that they learned more in one episode about Big O notation of coding blocks than they did about 2 semesters in college of it, that's amazing, and I feel you. I was there.
You get a refund, man.
Wait, that's an option?
Yeah, right.
No, you guys didn't go to Costco U? All right, a quick update from I think it was the last episode where we talked about C# strings and how they kind of dedupe the memory and usements of performance optimization. The technical term for that is actually string interning, and I didn't realize that's actually kind of common in a lot of languages, so you can read about it on Wikipedia. But I wanted to point out, great tip from Chumac84. He had a correction for us. It only works for string literal. So those are going to be strings that like show up in quotes in your code. So if you do something like, get date dot to string, even though that may have the same value in memory, it's not going to get the same benefits as you would as if you had that thing in quotes. So I just thought it was kind of interesting, and he sent me a little code snippet that was really cool. So really appreciate that. We love getting that feedback, especially when it results in us learning something.
Yep. Wait, I want to be clear there. We're talking about hard-coded strings.
Yeah.
Okay.
Yeah.
That's basically what you're talking about. And by the way, we've gotten some really, really good comments on the past 2 data structure episodes.
Mm-hmm.
So, I mean, we're not going to cover everything that the people shared up there, but there's some really good things about, why unmanaged code is faster than managed code and some of the reasons behind it and all that. So, if you want to go continue the conversation and learn some more, definitely head up to, /episode 94 or /episode 95 and take a look at those, because there's some great comments up there. So.
Yeah, so continuing on, this time we're talking about a couple more data structures. You want to kick it off, Outlaw?
Yep. So let's start with hash tables. So we've built up to here, right? We started with we started with primitives, so don't let me talk to you about floats again, because I will. But as we got into the more advanced data types, arrays kind of laid some groundwork there. So now we understand that arrays have their place. There's a lot of benefits to arrays, as a way of keeping a collection of data, but also like some of the performance trade-offs, right, that you might get. So they're great for lookups, random lookups, but if you had to like insert something in the middle, not so hot there. Versus the linked list on the other extreme, which were great for being able to insert or remove items from the middle of a list. But if you had to search or scan that list, they're not so hot, right? So what if we could live in some utopian world where we could get the benefits of both? That'd be great, right? Well, that's where the hash table comes in. So you get these kind of benefits with both of these, or with the linked lists and the arrays. You get that with the hash tables, but there's some trade-off. There's still some caveats. There's some things to be aware of, right? So, yeah. So I had here like the hash table smashes these two worlds together.
So hang on a second. When you say hash table, are you talking about maps or dictionaries or? I've seen these things used by bunch of different names in different languages. Are we talking about the same thing?
No.
No. All right.
No, I'm just talking about hash table. Well,
all right.
I mean, yeah, because that's the another thing that gets weird too. Is like, let's not confuse it with the talk of a language yet.
Okay, we're talking about like hash table data structures and like classic computer science.
Yes. All right. So, because there are like, depending on your languages, it might get a little bit more. The terminology might get a little bit more jumbled and mixed up, right? At least in the C# world, though, there are classes for both. So there's a separate class for hash table, a separate class for dictionary.
Yeah, we talked like for an hour on arrays and JavaScript and how they're not always arrays. So I'm not surprised the hash tables are no different.
Well, just on the naming thing, on the Wikipedia article, just to bring it up, it is also referred to as a hash map. So again, not getting into the actual implementations, whether it be Java or C# or any of those, they are sometimes called one or the other, hash table or hash map.
Yeah. So, I mean, specifically the MSDN documentation, they succinctly describe the hash table as the hash table class, as it represents a collection of key value pairs that are organized based on the hash code of the key. And even while they might be documenting their specific implementation of it, I mean, I felt like that was a pretty good overall description of what the hash table is and, what purpose it's trying to provide for you, right? So how does the hash table work? So let's consider that at the core structure of the hash table is an array. And within this array, each element of this array contains an object that contains the key and some value. So it's not just a simple like integer, at that key. It's some complex type of object, right? This now, if you're reading the documentation from like a Wikipedia, they refer to it as buckets. Some, I think in the Imposter Handbook, it was referred to as slots. There's not really like a name that I really liked for any of these. Like buckets super felt like a weird name. Like, why would you call it a bucket, not just like a name value pair or something else? I don't know. But a bucket seemed like a really weird name for what you would call that particular index within the array. But so I digress. So you have the underlying structure of the hash table as an array for a key value lookup. The data that you want to read or write to the hash table, you're going to use that data to create a hash, and that hash will serve as the index to the array. Right.
And I heard once a good example when I first learned about hash tables, and they were kind of trying to describe the purpose of the hash function. And the example that they started off with was not something that you would see in like production, like a real language. But the example I heard is like, let's say you've got a word, you've got English words, and you want to store them in a hash table. You may take the word that you're trying to store, take a look at the first letter, and then store it in a location based on that first letter. So, if the word is Abigail, then we're going to go ahead and take that first letter, be like, okay, this is an A, so let's go over here. Next word, let's say, is .NET Core. And we say, okay, that's a D. So let's put it over there with the D's. And then later when you come to look something up, say, okay, give me back Abigail, then we could go and look in the A's. And so it's really fast for inserts. It's fast for looking up things too. So it's just a good data structure. Now, in that example, it's a really bad choice because, if we add the word Alan in there, suddenly we've got two words now that both start with an A. And so we've got a collision.
Yeah. So this is where, like you're saying, the implementation of the hash table can vary. There's multiple implementations of them. And really what's changing behind there is like how they're handling collisions, the decisions they're making. So going along with your example there with Abigail and Alan, your hashing function in this case, in this example that you gave, is only looking at the first letter. So it picked A for both of them. There was a collision. So how does it put the second one in? So this is where, like, let's think of it being another, a linked list. So you have an array of indexes and then a linked list that a particular index, in this case, the index for A, would point to, and Alan would get tacked on to the end of that linked list. So when you want to look up Alan, you're going to go to the A's, then you're going to scan through the A's, and you're hoping that you're not going to have to go deep. You're not going to have, like, again, Joe's alphabetical hashing algorithm is probably not the greatest one. Sorry, Joe. So you're going to have a ton of collisions in that particular example, but let's pretend you didn't, because really the idea of the hashing function is that the collisions are going to be rare, is the hope. I mean, they're going to happen, but you definitely want them to happen less often than not. So that's the idea, right? Or can we agree to that structure? An array for the index for the hashes, and then a linked list for where the values are within there.
So is that every implementation of because, like, I don't know, they talk about collisions and there's got to be some sort of method to handle the collision. So is that the standard way it's done?
Okay, let's talk about, so you can't talk about hash tables without getting into a big conversation about the ways to resolve these collision strategies, right? So there's popular collision strategies, and if you go to the Wikipedia page, and there were a bunch in there, but what seemed to be like the two more popular ones were the separate chaining and open addressing variations. So in the separate chaining implementation, you would have those pointers, but when there's a collision, right, you'll traverse that list, look for your key, right? And so this is basically the example that I gave a minute ago. And assuming that you have a good hash function, you're rarely going to have more than 3 items in any given index. So, when you think about we talked about linked lists being awful, just awful for traversal, right? And that wouldn't be your greatest choice for doing any kind of sorting. But because these are so small, remember the article that we talked about that we referenced before, like everything is fast for small n, right? So it's going to be good enough in this particular example, because like if you only have 3 elements, that takes
assuming you don't have a bunch of collisions, which you should never have a ton of collisions if you have a good hashing algorithm. Basically.
Well, which is also another point too. Don't try to roll your own hashing function, right? Like if you can just use the library's hashing function, like if you had to create your own hash table, then if you could use a hashing function that's already built into either the operating system or the library or whatever that's available to you, you're probably going to be better off than if you tried to roll your own hashing algorithm. That's where you're going to get into trouble and have more potential for collisions.
Yeah, you want an even distribution, so, and you want like a wide distribution too, so you want a lot of different values because you want to keep those lists short. So the alphabetical thing is terrible. Like you're not going to get that many Z's, you're probably going to get a lot of A's, and besides, there's only 26 buckets. So the chances of you having more than 3 items in your linked list is is really small, depending on how many numbers you're shoving in there. I always did wonder what kind of hashing algorithms they were using. I've never really seen a good example of like, oh, hey, here's how .NET does it. It's based off of the memory addresses or something. So I just kind of wondered, like, with a hashtag with thousands and thousands of keys, like, what algorithm are they using to divide those up evenly?
And one other thing to point out here too is, while we're talking about this, there's this whole notion of collision, and that's because the hash can't be perfect, right?
Right.
And there is this notion in the Wikipedia article that's interesting that says the perfect hash function. So that can only exist if you know all the items ahead of time. So that makes sense, right?
Yeah.
If you know exactly what your data set is, then you can write the perfect hashing algorithm, which is not the case in 99.999% of the time. So these collisions we're talking about happen because you have a very good hashing algorithm that can't be perfect.
Correct. And Joe kind of hit on another good point too, that you want that ideally. Okay, so going to your point about you're not going to have a perfect hashing algorithm unless you knew all of the data up front. So then whatever best, as good as you can get hashing algorithm you want it to have an even distribution of where it's going to place things. Because again, going with that assumption that you're not going to have any more than 3 items in a given index within the hash tables array, internal array, right? In order to make that kind of assumption, then that assumes that your hashing function does create a good even distribution when getting random data to it.
Hey, one other thing I wanted to add, or I don't know where you finished. Sorry.
No, go ahead.
I just want to say one thing that's really important too is that hashing function has to be performant. Now, obviously, we don't want it to scale poorly based on like the size of the input, right? We don't want to have like a big, long, slow hashing algorithm. This thing needs to happen fast. If you look at like the big O cheat sheet or something and look at the lookup times and the insert times for hash table, it puts them at O of 1 constant time for fast lookup because it's assuming a good algorithm and it's treating that as constant time, which means that the bigger your hash table gets, it needs to keep about the same. And here we're talking about linked lists, which we know the insertion there and lookup time is going to be O of n, but they kind of cheat a little bit, and so there's like a little asterisk in the Wikipedias of the world, whatever they talk about hash tables, and they're like, well, it's basically O of 1. It's basically constant time for lookups and inserts in the normal case, but that's really not so much the case for the worst case scenario. But it just happens so infrequently if we have a good hashing algorithm, which is like this magical question mark, that we don't have to worry about it so much. And in practice, it works out really, really well.
And they say the average time is O sub 1, right? So the average. So that's why you can get away with that. And I'm sure Mike's going to get into some ways that it goes awry.
Yeah. So, well, before we go any further there, let's cover another one of the popular collision strategies, which is called open addressing. So in this implementation, the element in the array are the buckets themselves. So rather than the previous one where the elements in the array were pointers to linked list of buckets, in the open addressing, the item that is in the index is the item itself. Again, I hate the term bucket, but
that's what everybody uses apparently.
Yeah. So what this means is, let's say that let's continue the example of Joe's amazing first letter hashing algorithm. So Alan and Abigail, let's skip Alan for a moment. We only have Abigail in the list. And now Brandon comes in. So Abigail is in the first array index. Brandon comes in. He goes into the second because it's a B. Well, now when Alan gets inserted into the list, he would actually move Brandon down. So it would be Abigail in the first index, Alan in the second, and Brandon in the third index. So you see how this already got weird, right? The hash value only serves as a starting point for where you would look up the data from. So meaning that during a write operation, if you go to that index in the array and something is already there, you would continue on looking for an empty slot. Now, in the example that I just gave, I kind of smashed, Abigail and Brandon's indexes like right next to each other. And in reality, there would be some space there, but so that, because what you're doing is when you get to that first index, again, the index that your hashing function computes is just the starting point. So once you get to that index and you're trying to traverse from there forward through the array, looking for the next thing looking for the actual item you're trying to get to, you're only going to keep looking until you get to an empty slot. If you get to an empty slot, then that means that you never found what you were looking for, right? If you were doing a read. And if you were doing a write, then that would be where you would put the item, right? Does that make sense? So open addressing sounds awful to me in terms of performance. Yeah, I don't know.
I guess it's kind of unbalanced. Like, how long does it take you to look up an item in the worst case? So it's like, well, in the worst case, we keep looking at every little chunk of memory that could possibly kind of fit this thing. So it's, as you kind of start one spot, it's not there. Well, like either let me rehash it or let me look at the memory spot next to it or something like that, or some sort of method for determining the next place to look, and then you just keep looking until you're out of places to look. And that could potentially be pretty bad. So that seems pretty bad to me.
Yeah, it sounds bad, but it also sounds like even behind the open addressing thing, there's additional, features or ways to go about doing it. There's like several well-known ones: linear probing, quadratic probing, double hashing. And it's basically so you're not just going to the next one, you might be chopping it up, doing similar things like binary searches or something like that, so that you're trying to scan those indexes really fast, right?
Yeah, I mean, I imagine that the performance of it isn't that awful because you're only it's only for things that happen to hash to the same value
spot, right?
Which again, you're hoping that your hashing algorithm will be good and give you a good distribution, that you're not going to have those collisions often. So when you do, you're probably not searching a lot. So it probably, much like the separate chaining gets away with, traversing the linked list, open addressing probably gets away with having to traverse that array because there's not going to be that many collisions, or at least that's the assumption, right?
Yeah, assuming it's probably one of two things, right? Either assuming that the hashing algorithm is good enough, or that your data set isn't so large that you're going to run into those collisions more, right? Is my guess.
Yeah, because I mean, even if you had a lot of elements in the hash, in the hash's internal array at that point, assuming that there's a good distribution, you're only going to be scanning, a few items before you get to a space, and you're gonna be like, oh, there actually wasn't anything there, so that key is available. If that's where, like, if you try to get that value, you're just going to get back a null, or depending on whatever framework you're using at the time, however it decides to handle that type of situation.
Cool. I don't think we've really talked about what this looks like for the programmer. So I love hashes and their ilk because of how easy it is to use for like a programmer. So in JavaScript, I'm used to using it as an object. There's different ways to do that though. But I create my object and I throw the indexer, so the square brackets around it, and give it some sort of key. So I could say, Abigail is my key equals new person. And then I've created a new person, and it's stored in what I think of as being the key of Abigail. And then when we tell the hash, hey, give me the object at Abigail, then it's going to run the hash on that word Abigail there on my key. And that's how it's going to figure out how to look up the actual person in memory that I stored. And it's pretty awesome. So if you've got something where you want to be able to just kind of shove stuff in and look it back up, then that's a great data structure. I've been doing the Advent of Code this year for 2018. And one of the problems I just solved, I ended up using a hash table. And the reason I went with a hash table over an array, because I was storing numeric keys, is because I thought the data might be sparse. And this is something we talked a little bit about arrays. So if you've got like a fixed or a known size, say like 1,000, you could do an array with that. But if you know that you're only going to be using like, a handful of indexes out of that 1,000, then you're going to be pre-allocating a huge chunk of space in memory and only using, 10% of it or some small number. If you use a hash table, then you're only allocating the memory as you put the stuff in. So memory-wise, it's going to be really efficient. And the insert and take out times, the insert and lookup times are on average of 1. So it's going to be just as fast as an array for those lookups on new numbers, but much more memory efficient. Turned out I was wrong on that, by the way. It would have been much better to use an array in my case because it ended up not being sparse. So that's what I get for pre-optimization.
Yeah, like our previous conversation of like a list versus array.
Right.
Yeah.
Use
array.
that you shouldn't.
Right. Exactly.
Okay. So what are some other strategies? So the Wikipedia article has other strategies that they listed for hash tables, but they didn't go into quite as much detail. But so I'll just quickly like say some of the names like cuckoo hashing, hopscotch hashing, Robinhood. And then this one was interesting to me, the two-choice hashing, which kind of sounded like a rapper name. That would be like my rap name. I'm two-choice hashing. Be right next to 2 Chainz and what's up? So that one was kind of neat because like as the name implies, there's actually, it uses 2 hashing functions. And so if during a write operation, you find a location that is already in use, it's going to use the location that would, the hashing function's location that would provide the fewest objects already at that value.
So hash it one way, then flip it down and reverse it, and hash it again and see which one looks better, and just kind of go with that.
It sounds kind of awful from a developer. Like if you were the developer of that thing, though, of that 2-choice wrapping hashing implementation, it does sound kind of awful to try to maintain that code, because then you're like, just wrap your head around that for a moment. Like, okay, I just put something into the hash's internal array. How do I know which hash function was used? Like just trying to keep track of that kind of thing. Like obviously they've solved the problem. Someone solved it, right? Because it is a real thing, but
I would imagine it has extra storage needs behind the scenes, right? In order to map those things out. They've got a hash table to keep track of their hash table.
I feel like somebody came up with this at like the last second. It's like minutes to the deadline. They're like, oh, this is going too slow. No, I tell you what, just hash the stupid thing twice.
That's right.
And if one of them doesn't have an item, just put it there. And then whenever we need to look it up, we'll just do it twice. It'll half the time that we need to go crazy chasing down this crazy chain. Let's just go with it. And they tried it and it worked and they shipped. And now they're Google. I don't know.
Yeah, exactly.
And to be fair, when we said don't go writing your own hashing algorithms, we say that if you're just, writing some code. Obviously, if you've got a real use case for it, right? Like you're writing the next, network layer topology type stuff that's got to be crazy fast and you're not finding anything that suits your needs, and then probably you will write your own. But we're saying on general day-to-day type stuff, if you find yourself writing your own hashing algorithm, you're probably doing something wrong, right?
Yeah, there might be special cases where you know enough about your data set that you could kind of make an informed decision about that. And of course, if you were just wanting to learn about hash tables, like I'm really interested in how the heck they come up with an algorithm that works. Like this is not something I could do on my own. Like there's some math whiz out there who came up with this hashing strategy that was really good and smart about coming up with a good distribution. So I'd love to know what that is. So maybe one of these days I'll look it up and try to program it just like from an academic perspective. But this is not the kind of thing that you want to do on Friday afternoon before launch because, you want to do that. Just use whatever's built into your language.
Right.
Agreed. So we've kind of already hinted on this, but I just to go ahead and throw it out there, like officially, the complexity around hash tables and their usage. So in terms of space complexity, the average and the worst are just going to be O of n. So however many items you're trying to put into your hash table, there's your space complexity. The searching the hash table, inserting into the hash table, and deleting from the hash table are on average an O of 1.
Which is as good as it gets.
Yeah, that's amazing. And then the worst case is going to be an O of N operation. So it's awful, but I mean, it could be worse.
And this is one of those ones, like we mentioned, there's kind of an asterisk when you look up at a lot of times in the charts. Cause so often in Big O, we talk about the worst case scenario because it's kind of that limiting function deal. So that's kind of what Big O is designed for, is to let you know, like, worst case scenario. But in this case, it's so much more frequently the good case that whenever you do some sort of lookup, it's like they don't want to scare you. Like, listen, just pretend, just get it in your mind that it's O of 1. And then if you have a problem with it later, come back here and notice the asterisk and then look at it deeper.
And something, just if you guys, I'm sure we've all seen situations where just hundreds of thousands of items have been crammed into a hash table and it doesn't perform fast. So you're like, why? Because I would expect it to be really fast, because this should be a direct lookup. It should be an O of 1 operation, right? And then these underlying implementation details right here of when there's collisions and how those things are handled. Just imagine you're doing some sort of lookup, or you're looking up many items in that thing and it's having to go to it, but then it's like, oh no, now I got to scan the rest of the contents in here because there were multiple collisions. That's probably why you end up running into those things. So it's nice to know these things behind the scenes that are happening for you that you probably never even think about.
Yeah, or now that if you do have a slow performing hash table usage, maybe you have like some target to go after. It'll be like, well, what is it? Maybe there's something about my data that I'm not getting the uniform distribution that I thought I should have been getting. But just to point out though, that like when we talk about the best case or the average case, time complexity being an O of 1 versus the worst case being an O of N. I mean, O of N was like not far. Like O of 1 was a flat line, and O of N was like just
it's not terrible.
Like slightly, it was like maybe a 3-degree, 4-degree line. Like it wasn't a big line in comparison. I mean, we're not talking. It was definitely still at the bottom of the yellow on, like, if you were to go to bigocheatsheet.com, right? O of N is there at the bottom. So in your like quote bad cases, like it was the best of the bad.
Right.
I don't know. It still kind of stinks though. Like if you've got an algorithm that takes 1 second and then O of 1 with 1,000 inputs, it's still 1 second. But in O of N, even though it's great, a size of 1,000 is going to give you 1,000 seconds. So it's a big difference. And you can notice that if you ever had an algorithm that was like looking stuff up in arrays over and over and over again by searching through all of them, and you converted that thing to a hash table, you're probably going to see really big delay. I mean, a really big improvement there. But yeah, you're right. And it's definitely not as bad as the others.
Yeah, that's the point I was trying to get. I wanted to make was that yes, it could still be bad, but it's not like O of N factorial.
Well,
it's not a hockey stick is where I'm going with that.
Well, if you just really want to boil it down to that big O cheat sheet, O of 1 is the best. O log N is the very next best, and then O of N is the next. So you're not doing bad, right? You're barely out of the green. You're a little bit out of the green,
mm-hmm.
but still, it's not a bad operation. So the fact that your worst case is O of N is still not terrible.
But I mean, to Joe's point, should you find some kind of massive data set to where you have collisions 99% of the time,
right,
and you're using, say, like underneath the covers, unbeknownst to you, the separate chaining resolution strategy is being used, you're like, hey, why is my hash table performing so badly? If you happen to notice, like, oh, my data happens to just randomly be producing keys, hashes that are all, the same, that's why it's performing so badly, right? You could kind of like just make guesses, because even if you did happen to notice that it was producing that without looking at the implementation of the hash table, you'd be like, oh, they're probably using a separate chaining collision strategy behind the scenes, and that's why.
Yep.
Right? Now, who's actually going to go, start hashing all of their own code, their own data to see like, what it's going to produce? I don't know. Maybe you're using. Don't judge me, man.
Yeah. You do that. I'll be over here like npm install.
Right.
Hash 2.
Right. Exactly.
Man, you know what? I'm going to derail this for a second. I want
that never happens.
Right. I want to say how much better things like npm And I'm even going to give a shout out to the Java community.
Here we go.
And Maven
Oh God.
is the Nougat. Why does Nougat suck so bad?
Oh man.
Like seriously, why does it? I'm so angry at Nougat almost all the time because of this whole, it doesn't encapsulate its own dependencies well. And that makes me mad. NPM does it with JavaScript. Like how
is it an NPM? Is it a Nougat problem though, or an MS Build problem?
I don't care what it is. I honestly,
are you talking about like where A depends on B, B depends on C, C depends on D, and A doesn't have an explicit reference to D, but yet it's needed?
Well, that's one.
Because that's an MS Build. Let's be fair.
That's one. Okay. But the one that really irks me is all right, so we're going to dive down here into the C# world for just a second.
Let's do it.
So I am using Log4net 1.2 in my app, right? Let's say. But I pull in a dependency that's using Log4net 1.1. Well, guess what? I can't use it because I have to have the same dependency that my dependency has. And that burns me up. Like, dude, Maven and Java work really well in this world. You can bundle up everything you need in your jar and it just works. Why can't we make that happen?
Okay, two things. Number one is technically you could solve that problem with binding in your app's config. You could change the version, like you could give a range for the DLL binding and say,
let's say there's
anything
breaking
from this range to this range. Okay,
breaking
let's say that it's breaking. Number two way that you could solve this problem is as the publisher of that Nougat package, you could IL repack your dependencies in so that they come along for the ride. And they're baked into
bake them in so you're not actually including a dependency. But I still go back to the whole fact that almost everybody else has figured out this way to be able to bundle in your dependencies in a way that doesn't damage your own application. And it burns me up every time I face this with Nougat. Like it makes me so mad that I'm like, I'm not doing this in C#. I'm doing it in JavaScript. I don't care that I like C# better. I don't want to deal with this dependency entanglement nightmare, right?
Yeah, every time I deal with Nougat, it does seem like a bit of a headache. And when I'm used to using things like Node, it's a no-brainer that I can just npm install anything in like 2 seconds and get it working. Now the Node module folder is horrible. It's a nightmare to look at it. And it's like 300 gigabytes or whatever for the tiniest little thing. But, that's crazy.
But that's
other good stuff though.
Your tip last week or last episode, Joe, that Jamie provided. I mean, that was the whole point of even for NPM was trying to get around some of these problems where, if you only built based off of the package's JSON file, that's kind of loosey-goosey, right? As to like what the versions could be. Whereas the package lock JSON isn't. That's specifically, here's the entire dependency graph, like every version that was used, right? And that's where, while we're on this tangent, like even if you do the IL repack that I mentioned as a way to get around it, that's where those kind of solutions can still irk me, right? Because I'm willing to understand like the challenges that Nougat has. In MS Build, I kind of can't forgive for the like not including the dependency thing,
skipping the chaining dependencies.
But then that problem then carries forward or is replicated by, and I don't know which. It's either but by like IL repack, for example, where if MS Build didn't, so dependency A, or let's say app A depends on dependency B, depends on dependency C, and dependency C depends on dependency D. And MS Build, when it does that compilation, if app A isn't explicitly using dependency D and nothing in its execution path is using dependency D will not come along for the ride.
And then you'll be missing.
So
the reference.
in your bin directory or your output of the compilation process, you're not going to have that dependency there, right? Well, you and I especially, I know, have seen cases where, and it's well documented, like you go search it on, like Stack Overflow has plenty of articles on this problem, where even though it thought that it didn't need it, it actually was needed, in some scenarios, and, you'll get runtime errors that you won't see. But IL repack to its credit, I guess, instead of making it a runtime error, you'll see it as a build error, because it's not smart enough to recognize the dependency that app A doesn't use certain things. And so if it sees that one of those random dependencies has a dependency, the next dependency, it'll keep walking that app's dependency chain, expecting all of those DLLs to be in there so that it can hack them all in together. And when it can't find D, it's like, oh, well, we're done. All right. Well,
there's such different cultures too. I just had to mention, like, when I'm working in front end, like, I mean, I'll require something in like a heartbeat. Like, oh, I don't want to left pad this thing. Just look it up. Like, nobody cares, because it's the front end. For some reason, I guess maybe because there's like this culture of kind of these things being small and like singular purpose, and DLLs tend to be heavier. Man, when you're working on the back end and you want to bring something in Nougat, it's like, all right, let's call the tribes together. Let's get the council, all the dev, managers get together. And you got to go there. You got to bring presence, and you got to sweet talk them, and you got to set up a recurring meeting, because it's probably going to take you a couple to actually get this thing added to the project. And then when you finally get around, everyone, or 80% of the people agree, yes, let's bring this package in instead of rewriting it. Then you do it, and then it breaks the build, and you got to mess with it for the next 24 hours until it actually works.
It's so true too. Like, you've got the Senate over here,
Yeah.
you got the House of Republicans over here,
Yeah,
you got Congress, you got veto power.
See, I thought when you said the Senate, my mind immediately went to Star Wars, and I was thinking of the the Senate within Star Wars.
Oh gosh.
So I was picturing like that kind of room, like you go out on your little hover
floating platforms.
Yeah, your hover platform to make your speech about, like, we need this great library.
Yeah.
So yeah, man, I apologize for derailing. Something snapped in my head when you said something, and I was like, oh no,
it was like you had a twitch, like you hadn't had your medication yet.
It's one of those things like where you fight it, you just like, at first you're angry and then you're confused, right? Like, why would anybody ever let this happen? And then it's just,
I think it's backwards, right? Like, you're confused, like, wait a minute, why is this broken?
It might be
work.
It might be many stages.
What DLL is that? I'm not using that. Like, there's no reference to that. Why is it complaining about that? So yeah, you definitely start out confused, and then when you realize what the problem is, then you're angry, and you're super angry. You're like, what?
And then you're like, you know what? I'm going over to Java. I may think it's way more explicit than I want it to be, but I'm about to change, coding paths in my.
Whoa. Now you're talking emotionally, because that is not a rational decision. Just come over to JavaScript, man. Seriously, if I want to uppercase a string, I just npm install uppercase. I don't even care that it's built into JavaScript. I'm just going to get the package. And if it's mining some crypto coins in the background, then whatever. That's the price we pay. Someone will fix it eventually.
Oh, that's so amazing.
I'm going to assume that some of our Java brethren are, among us here, are going to be upset.
Yeah, they're already upset.
Yeah, don't hate us.
We've been in Java all day.
We don't hate you. It's funny. There are definitely things that are way more polished and more better in the Java world.
Well, come to Microsoft Land. We got Link.
Oh, that's so beautiful. That almost makes up for all of it. It almost does.
Well, I was going to say too, like, I don't know why in my reaction to like that situation, like, you would suddenly in this hypothetical situation turn into Little John.
What? What? Oh man!
And then when you do finally get it to build, I mean, Little John comes back at me. You're like, yeah.
And you're over there like high-fiving yourself in the corner, and everyone else is still pissed.
Yeah, exactly.
Like, you broke the build all day, and you're high-fiving yourself. Great.
You're like, you don't know where I've been.
Yeah.
I got some of my Little John impersonations apparently, though.
Yeah, that's good. Killer.
Those are hard ones to do, man. He worked on that for years.
All right. Let's get back to hash tables and all the fun that they are.
Yeah, sorry about that.
And so quickly, let's talk about like the pros of the hash table. The speed, number one, by far and away, the speed of the hash tables. The reads, ignoring collisions, you're generally going to consider that an O of 1 operation. If there is a collision, the read-write time can be reduced to n divided by k, where k is the size of the hash table, which can just be reduced to O of n. Don't you love big O notation?
Just throw everything away.
There should be like a whole like big O math. Like,
it's basically drop all the constants, right? Like, that's
Oh, you had some operation in there?
Don't worry about it.
Nah.
Details.
Whatever. N divided by K. Nah. All right. Assuming a good hashing algorithm is used, it's usually going to be O of 1, like we said. And but this assumes that by the good performance of the hash, that by good, the performance of the hashing algorithm has been considered. So to Joe's point, if your hashing algorithm is going to take a second and you have to put 1,000 things in this hash table, that's not going to be a good hashing algorithm. So yeah, I mean, you can't blame the idea of the hash table at that point because you have a bad performing algorithm. So even if you do have a slow algorithm, it might still be O of 1, but it may be slower than the alternatives.
And I think that's worth explaining, right? It's O of 1 because the lookup operation itself can go directly to it, but the hashing behind it is ridiculously long and tedious. So, yeah.
All right. So to the cons of the hash table. So depending on your language, I'm looking at you, C#. The hash table type is loosely typed. We'll come back to that in a moment. The cost of the hashing function can be more than just looping over the list, especially for few entries. So, if you only have 2 items in your hash table, did you really need a hash table? Right? I mean, probably not. Maybe. Probably not. Because the hash table entries are spread around, there is a poor locality of reference, which can trigger processor cache misses. So, again, if you're trying to squeeze every bit of performance out, cache performance can also be poor or ineffective depending on the implementation, such as separate chaining. And the performance can degrade when there are many collisions, which, we pretty much already covered that. All right. So when should you use a hash table? So now, if we are talking about specific language implementations of a hash table class or type, then don't. At least not in C#. Like there's, you should prefer the dictionary type over the hash table type.
Every time.
And not in Java either. You should use the hash map.
Isn't that interesting?
Yeah.
Yeah, because it's strongly typed, and so the alternative is if you use the hash table, then what happens is you're going to get an object back and you're going to have to cast it. So you're losing the benefits of having a compiled language, right? There's no sort of checking around that, and potentially you're doing something wrong or getting an error. So that kind of stinks. And if you're storing simple values, it's even worse because you're going to end up boxing them. So you're going to take these simple values that would take, say, 32 bits for an integer, and then you're going to stuff them in a 64-bit reference and throw them on the heap. And then now you're taking up whatever 32 times 3 is, 96.
It's not just taking them up. Now you've also got the garbage collection and everything else on top of it, right?
Yeah. And totally unnecessary if you just use the strongly typed version.
Right.
So if we're not talking about the specific language implementations, then when should you use the hash tables? Okay, so anytime you need an associative array, so by that I mean you want to have an array, but you don't want to necessarily look up items in the array by their index. You might want to be able to say like, hey, in this array of people, I want to find the Allen object, right? That's what I mean by the associative array. There were other examples that were given too that I found that were like database indexing, or another good one too would be cache. If you wanted to build your own cache, you could use a hash table behind the scenes so that when your user wants to add something to the cache or look up something from the cache, you hash the value that they give you as the key, then go into that point in your hash tables array and find it. And then sets was another option when you might want to use these.
I think it's worth calling out cache specifically just because that's a very common use case for it. If you're doing like something, a REST API, like one common approach might be to get the REST call and you take those arguments and you kind of put them in one big string and say, have I seen this in the last 30 seconds or something like that. And then if you've seen that, if you've got that object in the hash table memory, then you can go ahead and return it without going and hitting a slower service. And so it's really common to use it in those type scenarios, and it's all about coming up with and managing those keys. Then on your end, in the background, this should be using a really fast, efficient data structure for storing that data.
All right. So it's that time of the show when we ask you, if you haven't already, please do go leave us a review. we say that it puts a smile on our face, and it totally does. And actually, somebody left us a review that said they left the review to put a smile on our face because we put one on there. So, that's awesome. I mean,
wasn't that nice?
That put a smile on my face. Imagine that. So, yeah, I mean, if you ever find yourself and you're in front of your keyboard or on your phone and you're bored and you're thinking, hey, you know what? I meant to leave those guys a review. Please do. It makes our day, and we really appreciate it. And it's a nice way to give back. So, thanks.
Yeah, and also too, we greatly appreciate the reviews, like Alan said. But you could also spread the word, share Coding Blocks with a friend. Let one of your coworkers know about the show. Expose more people to it.
And inevitably, you're going to say, yeah, there's this podcast. And somebody's going to look at you sideways and be like, what's a podcast?
Yeah.
And then you can explain to them, oh, it's really not that big of a deal, right? So, yeah, it's even a good icebreaker for people that haven't been introduced to the podcasting world.
It's like TiVo for radio.
That's right.
What's TiVo?
And then you can turn them on to Serial and Hardcore History and a bunch of other things that they'll love. So, yeah.
Yeah, you could definitely be the life of the party. You're like, oh, God, here comes the podcast guy. He's going to tell us about Coding Blocks again.
The podcast guy.
I've been that guy.
All right. Well, whoa, excuse me.
Yeah, you got to be ready to do this. You can't mess this part up.
Yeah, I can't mess this up like my Little John impersonation. So this is time for my favorite portion of the show. Survey says. All right. So in episode 94, we asked, what do you value most in a job? And your choices were pay. It's all about the Benjamins. Or tech stack. I need to remain interested. Or commute. Or the lack thereof. I mean, I love listening to Coding Blocks and all, but a new set of tires every month is ridiculous. Or location. It's just like real estate. Or team. I need to be surrounded by people better than me so I can grow. Or industry. I want the type of problems I solve to matter to me. Or benefits. I like to take off for the summer. And lastly, work-life balance. I have a life outside of the office. All right, I believe Joe went first, I think. So let's start with you, Alan. What do you think?
Man, this one's tough because there's a lot of, I'd say a lot of these, at least personally, speak to me. I'm going to go with, for most people, pay. It's all about the Benjamins.
Okay.
I'm going to say 35%.
Okay.
All right. Yeah. And for me, I think that location's going to be the biggest factor, either wanting to work from home or having something where I'm going to guess that most people don't want to move unless there's plenty of Benjamins. But I'm going to say location at 30%.
You both are committed to your choices. Alan with pay at 35% and Joe with location at 30%. I have that right?
That's correct.
Drum roll, please.
We're both wrong, really.
Yeah. I'm super surprised, and I'm curious to see where you're going to come in on this, Alan, because you were super opinionated, and we're just dying to spill your opinion on this at the time when we were doing episode 94, if you recall. But no, work-life balance, far and away 30%. Everything else was kind of scattered among it, but yeah, it was clearly, the one that walked away with it.
That one I thought would be up there. I didn't think it'd win. I wonder if that's because everybody's already paid well. So now they're on to
maybe. Yeah, if you listen to this show, then you're in the A tier, so you're already making the bucks. So yeah, it's about that work-life balance. So chances are, if you're listening to this podcast, it's 2.5 hour podcast while you're on your downtime, while you're commuting or washing the dishes or whatever, then chances are you're working too much.
Yeah, it's I don't know, man. For me, commute's a big one. Right, living in the Atlanta area and knowing that you can give half your life away to the gods of the highway. So
is that what we're calling them now, the gods?
Yeah, I guess. Yeah,
American gods.
I honestly thought
then I smite thee.
What was number 2? So if work-life balance was number 1 at 30, you said.
Yeah, I mean, then from there, tech stack was surprisingly
Number
Wow.
two at 21%.
Wow.
Well,
That's shocking.
team was close though at 20. So there
Really?
wasn't a big difference between those two.
What was the lowest?
That one was like so hard for me because I'm like, really? Because how do you judge the team unless you know because they're already friends of yours,
Right.
or people that you've met or whatnot, and so you kind of already have an idea of who they are. Unless you're just making an assumption like, oh, it's Google, so I just assume they're going to be like, a bunch of smart people, for example, that, but otherwise it's like, well, how do you know who the team is to use that as your determination? I don't know. I personally thought this was going to be a silly survey. I thought far and away the winner will be pay. It'll be like 98% pay. And like two people are going to make a joke about something else, right? But I was really surprised to see that, pay didn't rank as high.
It honestly, you know what? And maybe this is just something about our audience is I'm wondering if a lot of it really is people are getting paid pretty well because they've taken the time to invest in their skills by listening to podcasts or reading books or doing courses or just constantly improving. So that's almost like, yeah, that's coming right now. I need to focus on what else is important to me. That's
if you're in our Slack, then you can go to the salary survey channel, and we've got a little survey there, so you can go ahead and you can already see what people put in there. Of course, it's all anonymous, so you might be interested in that.
Yeah.
What was the lowest though? I have to know.
Yeah.
I'll tell you, but I did want to just finish up this one thought though. Along that line though, you kind of hit on something that maybe it's just our industry that, maybe we're asking the wrong industry. So maybe people within our industry, these are the things that would matter, and like work-life balance may rank higher. But if you were to go maybe across industries, then maybe pay would rank more. If I guess what I'm saying is like if the industry was more general purpose or across all of the industries, then maybe pay would rank more higher, or maybe I wouldn't be surprised, right? But to your question, benefits was the last, and I think that's what you would have said. That's what you were wanting to say last time, Alan. Am I wrong? Was benefits not the...
I don't think, no. I think for me, it was probably going to be either commute or pay. I was pretty sure it was going to be one of those two.
Oh, really? I swore it was going to be benefits.
Yeah, I mean, the benefits thing is always, I don't think it's ever anything somebody's like striving to get the best benefits, although it could make or break the deal when they go to a particular spot, right? So I don't know.
Yeah, well, it's really interesting. So Good to know.
All right. Well,
and by the way, you can see that whole pie chart by going to the show notes and voting. Then you'll be able to see actually right after you vote.
Episode 94, is that right?
No, for that one. Yeah, that was episode 94.
Yep.
Yeah, and all surveys that we do, once you take the survey, you see the results of it. So you don't have to wait so long to see the at least a few results.
Although it's much funner to hear it.
Yeah, sure.
All
right. So I was at Data SciCon last week, and they had obviously there were all kinds of amazing talks, but there was one little thing that I was like, oh, this is going to be so fun. I got to save this for the show. So a little fun, quick game that I wanted to play with you two, just to talk about the magnitude of data. So this comes from, I'm not going to tell you the source yet because I know Alan's already at the keyboard. He's going to go looking for it.
I would never.
What? I just saw him reach for his mouse. But so if we talk about, if I were to ask you how much data is generated every minute,
Ooh.
All right? And this is as it relates to 2017. How much data was generated every minute? Let's talk about first, what would be a big one? Okay, here's a good one. Let's pick Amazon. How much money in sales did Amazon make every minute for 2017?
Golly.
Oh, it's going to make you sick.
100 million.
100 million every minute.
In sales. We're not talking about revenue. We're talking about
sales.
Not yeah.
Million a minute.
Wow. Jeff Bezos would really like you guys' number. It was $258,000, $751.90.
That's
Okay.
nothing.
I way overblew this one.
Yeah.
All right.
Yeah, you
I
guys,
figured the costs were high.
overshot it by a multiple of 4. So
Like
if that's-
everyone at Data Science Con was shaking their head right now. It's like,
Yeah.
you guys.
if the rest of these are going to go like this, you're going to be depressed by every answer I give. So I'm just going to throw that out
All
there.
right, we're gonna shoot further down.
Okay.
800 petabytes. Okay, no, sorry.
Okay.
Go ahead.
How many tweets per minute did users send on Twitter?
$400. Wait, what was the question?
750,000 tweets per minute.
750,000?
1 million.
456,000 tweets per minute went out across Twitter.
Wow, that is pretty crazy.
That's a lot.
I understand tweets. I don't understand dollars.
Yeah. Here's a couple of interesting ones. What about how many spam emails do you think were sent every minute of every day in 2017?
750,000
Is that going to be your answer from now on?
How many spam emails sent per minute?
per minute. Yeah.
10 million. No, actually, I'm going to say bigger. I'm going to say 100 million emails.
Come on,
spam
dude.
emails per minute. Absolutely. I at least get 1 million a day.
Well, I'm going to put it to you like this, and I'm going to break your heart because he is way closer than you were.
Wow.
Way, by orders of magnitude closer. It was 103,447,520 spam emails sent every minute of every day for the year 2017.
Dude, that's ridiculous. How is the internet even running? Because that server's relaying that stuff. Oh, man.
Let me put this into context for you. This is really going to make you feel depressed about the use of the internet. There were, for Google searches conducted, there were 3,607,080 Google searches for every minute of 2017.
Wow.
And it was a factor of.
There's 100 million
30.
more email spams being sent than there were Google searches.
Good Lord.
That's crazy,
Wow.
right?
That's ridiculous.
Let me tell you, if they use my definition of spam email, which is just about anything that wasn't sent from a human to a human, then it would probably be way higher. Yeah.
Man.
So here's one that I didn't expect to see. How many forecast requests do you think that the Weather Channel received?
Ooh. Just for total for 2017?
For every minute. We're doing every minute. Every one of these
still.
questions is going to be relative to a minute.
500,000.
500,000.
2 mil.
I gave you guys a hint by saying that I wasn't expecting this one. It was 18 million
Wow.
and 55,555 requests every minute.
Jeez, man.
I got 3 devices on my desk on right now, 4 that are all probably checking the weather right now.
Right.
All right, let me. I don't want to go through every one of these, so I'm going to pull out a couple more. So I got 3 last ones that I want to say. All right, YouTube videos watched per minute.
In 2017?
Yep.
Minutes watched per minute.
5 million.
$400. Wow, 1 million.
Joe wins. $400 was the correct answer.
Yes.
No, you're pretty close, Alan. 4.1 million.
Nice.
Yeah.
And that number's just went up.
Yeah, sorry. $400 is how much they pay out per year to people who post their videos there.
What about text messages sent?
10 million.
Per minute? 10 mil.
Oh, you're both going 10 million. Okay. I like it. 15 million text messages per minute.
Wow.
I'm rounding down because there was some more to that number.
Right.
Last one. that I'll say. I'll include a link to this in the show notes, but the last one that I've got here is how much data did Americans use of internet data?
Per minute or like total?
No, this is every one of these is per minute for every day of 2017.
What was the question? How much
internet data did Americans use every minute of every day of 2017?
I don't know the numbers, like 250 Potter bytes.
petabytes? Potter bytes.
The one after that.
Oh,
The Harry Potter bytes.
Harry Potter bytes. I'm gonna go with 10 terabytes.
Okay, so they put the number in terms of gigabytes, and so that's how I'm going to read the number. It would be 2,657,700 gigabytes every minute of every day.
That's what I said.
I know, Joe, but I couldn't give it to you like that. I had to take some of the steam away from you.
Yeah, the translation is magical. That's crazy, though. That's crazy.
Right? Yeah, I thought you guys might enjoy that a little bit. So again, there'll be a link to that in the show notes. So the listeners can play along at home.
Hey, so you said that was 2 million gigabytes, right?
Yes.
That's 2 petabytes is what that is. I just did Google Translate. So just in case the next one after it is not the Harry Potter byte. It's the pebabyte. Never heard of it. So the pebabyte.
Yeah, because I should have thought about that. Yeah, you're right.
Yeah.
So next time you're mad at your cable company or whoever you're getting internet access, just remember what they're putting up with.
Oh, you're paying for this, man. You get all of it.
Oh yeah, I'm shilling. They're sliding me them dollars under the table for repping.
All right, so we'll wrap this up by saying that today's survey will be, we're heading into the holiday season, so you got to start making some important decisions here. Namely, how do you plan to spend your time off this holiday season? And your choices are spending time with the family, because the holidays are all about the memories. Or, I'm not avoiding the family, I'm building my next great project. Or, escaping the family and the keyboard. Or lastly, wait, what time off?
You have you guys got in your minds what the answers are going to be?
You can't ever do that.
No, we're not gonna tell it. I'm just wondering.
Well, I know my family's not listening, so I feel like it's okay for me to say that I plan on spending a lot of time with my computer. Because the computer's always listening, by the way. So you should never talk bad about it.
That's right. Hey, you guys want to hear a roof joke?
Okay.
The first one's on the house.
Oh, God.
Oh, boy.
Oh, yeah, that's right. There were some jokes that we had, too.
That was really awful. That's great.
What do you call a pile of kittens?
Perfection?
A meowton.
Oh, boy.
Here's one. Why are teddy bears never hungry? Because they're always stuffed.
Oh, boy. Well, in the interest of being done before 3 hours this episode, move along.
These are ones that you can share with your family. They're safe. All right.
All right. So now we're going to talk about dictionaries. And much like the hash tables, actually, they're pretty much the same thing as hash tables. The main differentiator being that hash tables, the definition in the Wikipedia computer sciencey definition of the hash table data structure, the dictionary holds key value pairs, and those values are untyped. So a dictionary is the same thing, except we know what type it is. And so there are a couple little shortcuts that we can take because we know the size of that ahead of time. And like we mentioned earlier when we talked about hash tables and C# and Java, there's no good reason that I'm aware of to use one of those untyped data structures when you have a strongly typed option available. If you're working in something like JavaScript, you don't really have this sort of differentiation. It doesn't Makes sense because it's a weakly typed language. But in something like a C# or I don't know what C++ has available here, but anything like that, you're going to want to use that strongly typed option if you can get away with it. And you pretty much always can. I don't think I've ever used a hash table in C#. What about you?
Ever? Oh, definitely. Yeah, back in the C#, I think it was before.
Pre-generics?
Yeah, they didn't have dictionaries. They didn't have the typed ones, so all you had were hash tables back in the day.
Yeah, and you just cast it on the way out?
Yep.
Yeah, that stinks. Yeah, and so they even look really similar, and in C# you do like a hash table, or var my thing equals new hash table, no types there. Dictionary, we've got generics, which we mentioned. And if you're not familiar with generics, basically you've got these cool little angle brackets where you specify the type. So you say a dictionary, and my key is, say, an integer, and my value is a string. And you can change those items in the brackets. So it's the same class underneath, it's dictionary, but you're changing the strongly typed arguments that can go inside of it. So we could say a dictionary with a string is the key, and a person is the value. And you can get even crazier. You don't have to use primitives for that first type. You could say my dictionary has keys of a person, and the values are strings. So kind of interesting. I don't think I've ever used a complex object as a key before. I don't know. Is that?
Well, I mean, would you call a string a complex object though?
No, I mean, it's not a primitive, so I guess it is. I definitely use strings there. I was just trying to think like a customer object or something like that.
I think I have. I'm pretty sure I have. I can't think off the top of my head why, but
Would tuples count?
something like that is kind of where I'm thinking. But yeah, if you had something like a customer object or an order object, right? Then
Yeah.
it's something that you're trying to associate with it in your dictionary.
So if I've got like some sort of code that takes in a bunch of customers and it counts up the number of orders, then I might have a hash table. And as I loop through the orders, I might say, okay, this customer, if I've seen him before, just go ahead and add to the number of orders. If I haven't seen him, go ahead and initialize that spot in the dictionary with a value of 1 for that order. And so as I loop through the orders, at the end, I'll end up with something that I can say, hey, dictionary at customer Abigail. They have 3 orders. That's going to be a fast lookup, which is really nice. And so in that case, I guess it is nice to be able to use that complex object. So I can just say, just take the whole customer object. And then that way I don't have to have like a separate data structure where I say, okay, the dictionary has the string Abigail that uniquely identifies as customer. Then I go over to some other dictionary and then look up the object based on the key of Abigail there again. So that would be pretty awkward. So I guess it's really nice. I've just never really thought to do that.
So I'm kind of curious then, because the way you started with like the hash table versus the dictionary, right? And it was about like the specific implementation though, like specifically in like a C# implementation, right? Where like hash tables, are based on object and dictionary are based on generics, right? But what about well, I mean, for example, in the imposter's handbook, right? Like he says the specific difference was that the dictionary, I don't know how, but is able to guarantee that it's going to have a unique index. Each item is going to have a unique index. So therefore it's O of 1. That was the performance gain of the dictionary over the hash table.
So I can tell you a little bit about that. From what I've read, specifically in C#, that is the case. And I'm not too well versed in the whole, underlying implementation, but I do know that underneath the covers, there are differences with these two data structures. So Wikipedia definition-wise, the only difference between a dictionary and a hash table is that a dictionary is a strong type and you should use it. Now, implementation-wise, if you look under the hood in the CLR for C#, then or you just read about it, that's the way to really do it. We'll have some links there. Is that the hash tables, that's the untyped versions, they use a rehashing scheme. And so we kind of talked about a couple of those earlier, where it basically says, okay, the spot's full, let me try rehashing it and find another spot, and I keep doing that until I find an open spot, and then I plunk my item in. And the dictionary uses chaining, which is like the linked list idea, where we say, okay, we've already come to this bucket before, let's go ahead and chain the items. However, under the covers, C# for whatever reason, I've never really found a good reason why they did this, but in the way they implemented their hash table, they made certain to have an underlying data structure that had one bucket for every item in your hash table. And so they end up more or less guaranteeing that you always have a short number of items in that list. Does that make sense? So if you have 10 items in your hash table, you've got 10 buckets. If you have 1,000, then they give you 1,000 buckets and they hash your key down to one of those X number of buckets. And so it keeps the ratio really good, or close to 1, I guess. So the number of available buckets is always equal to the number of items that you're storing.
I mean, where I was kind of getting like tripped up mentally in my own head was just that in the book that we referenced, the Imposter's Handbook, there wasn't a lot of detail about that implementation of it. So I was like, well, that's a bold claim. Like, did it? I mean, I'm not saying that it's wrong, but that the dictionary has a unique key for accessing any given value, like that you're not. According to the book, there's not going to be a collision in the dictionary. So conversations about like chaining, separate chaining, or open addressing, or rehashing are moot because there's not going to be a collision.
So what I read was basically that the length of the list that it uses underneath that it uses to store the collisions is never going to exceed the bucket size, because the buckets are always guaranteed to have the same number of buckets as you have elements. So it ends up basically keeping a good ratio, a load factor, I think they called it, of nodes to buckets that ends up, mathy hand wavy stuff ends up keeping the ratio really low. And so you can never have more items in the, wait, am I saying this right? You can never have a longer list than you have buckets.
So,
and I'm going to do a terrible job of explaining this because it was way over my head and very complicated. But that's kind of the secret there of like how they end up guaranteeing performance for the dictionary. Is they basically have a specialized algorithm where they keep a good ratio of the length of the list and the number of buckets. But as for how they do that, that's way over my head.
So here's something interesting on Stack Overflow about the collisions with dictionaries and the fact that how they're handled. Basically, it uses get hash code. So the answer is basically saying, don't assume that whatever you could even do like an IL peek on these type of things and look at what the implementation is, but don't think that that's what it's always going to be, right? Like they could change it in the next version of .NET, how they implement it. But they're actually saying that if you have an object that's being put in there, the get hash code method must return the same value for the lifetime of the object, right? So that's basically how they're ensuring that these things go to the right place. So the equals and the get hash codes are the important parts of this.
And so when a collision happens, we store more than one element in the bucket, which affects the time we need to look it up, because we need to traverse this linked list in order to find our item. Now, in order to make that look up fast, they keep the ratio of the number of the items in the list and the number of the buckets in the container low. That's the magical mathy part that I just don't understand. I've looked at the algorithm a couple times and read a couple of articles, and I don't understand why that ratio is important or why it guarantees things are fast. But I did not see anything that said that you wouldn't have a list. Like, in fact, I did read a lot about this special kind of load factor that definitely refers to the length of the list in comparison to the buckets. So we'll have links though. So I definitely.
What were the nodes again? You had the nodes and the buckets. There was a ratio of the nodes to the buckets, but what were the
load factor?
The node, the load factor?
The load factor.
Well, the load factor is the ratio of the nodes to buckets.
It's the ratio of the length of the list to the number of buckets.
Oh, okay.
So if you want a 1-to-1, right, is what you want.
I got you. Yeah. What Alan's saying. Either that or you want it to be uniform is what we're saying. So if it was like going back to the hash table definition that I gave earlier, right? Like if the underlying structure was an array, then at each index in that array, you want it to be a uniform thing that are in each of those indexes. So each one of those indexes is a bucket, right? And if it was like a separate chaining, then you have a linked list of buckets per index in that array, right? So you want the number of buckets being pointed to by each index in the array so that it's balanced, right? So the load factor should be
close to 1. And what I read is that the way that they kind of manage it and the way that they do the chaining is set up is so that they add a new bucket every time you get a new item. And they do this in order to keep that ratio positive. As to how they guarantee things get split up correctly, I just don't, I plain flat out don't get it. I don't understand what adding more buckets has to do with making things faster, other than it improves this load factor number because the number of the buckets is now getting higher as the potential list of the length of the list is getting higher. So it keeps that ratio really, I guess at worst 1, but I don't understand why that's desirable. We'll have some links in the show, though. I mean, I don't think it's something we're going to figure out because it's definitely pretty hairy in there. There are some really nice articles on it. And if you understand it, Chumac84, I'm looking at you. Could definitely use your help on trying to figure out why. Because what I'm thinking is there's a decision that Microsoft made here. And so we've got hash tables over here and dictionaries, and we're choosing to implement dictionaries, the one that came out later, differently. So either that's because they figure out that chaining is actually better, but they didn't want to change the original implementation for backwards compatibility reasons. Or they said, you know what, because the dictionaries are strongly typed, we can do a little bit of extra mojo that helps us balance things better and, you know, maybe allocate stuff in a different way. Like maybe that's why they can create those buckets of a uniform size and know what it's going to be like. I don't know the answer to that. That's just me speculating. I never did find authoritative sources that, hey, dictionary does it differently because it's better. And they could.
I am curious though, because like one of these has to be wrong, right? Like, you know, because that going back to the book, it was saying that it says the dictionary is exactly like a hash table, except it has a unique key for accessing a given value. And so the collisions are not something you have to worry about with a dictionary, right? But yet, you know, to your point, like the documentation from Microsoft says, you know, it talks about employing alternate collision resolution strategies. And even I questioned, like, how could you guarantee a unique key? Right. Like, how could that possibly work? So my inclination is to think like, well, I guess the handbook might be wrong about that part, or maybe I'm misunderstanding that part. But then on the other little, you know, I got like a little devil on each shoulder, right? And so the other one was saying like, well, I mean, when Microsoft decided in .NET 2.0 to create the dictionary class, they could have just said, well, we already used the Hashtable class name. So we already have a class named Hashtable, and we want to have something very similar to it. So I guess we'll call it dictionary, but maybe they really implemented a Hashtable behind the scenes. You know what I'm saying? Just similar to how like in Java, they started out with the Hashtable, and then they decided, I don't remember the version, to create a better version of it, and they call it the hash map, right?
Well, I guess thinking out loud a little bit though, if you add keys, like if you knew up a dictionary and you try and add a duplicate key, if it's a number, it'll yell at you, right? Like it's like, no, you can't do that. If it's an object though, it would have to rely on the get hash code. So I don't know, maybe you don't have collisions for primitive type keys. I'm not sure. Did you
I mean,
see
the computer sciencey though definition. Well, if we're taking the way it's written here in the handbook as the quote computer sciencey way, right, where there's not a collision,
right?
I mean, then it's not. Yeah, I don't know, man.
Yeah,
I'm taking this thing at face value, but maybe that part is not accurate.
Yeah, I mean, looking at the Microsoft docs, it doesn't sound like, and I mean, I don't know.
But I don't know how to make that. I'm not trying to decide like what do I make of that? Are they talking about specifically from the name of their class, right, and how they implemented their class, or are they talking about like here's how the computer sciencey definition of a dictionary? Yeah.
Yeah. So my takeaway is that the Microsoft documentation like clearly says like, hey, we do chaining for dictionaries and we do rehashing for the hashes. So, everything I know about chaining says that it's using a linked list underneath. So maybe they're just getting a little loosey-goosey about what they define it to be a collision. Like maybe they're saying it's not a collision because no matter what, you're always getting a pointer to a linked list back. And so you don't really know if you're colliding or not. You basically get a pointer and you throw it on there. And so when you go to look stuff up, then I'm speculating again, but I don't really know why there would be a discrepancy between the book and the documentation, but I have no reason to think that the documentation is wrong. Like there's several articles and stuff that I read specifically on that keeping of the list.
Yep.
So I don't know, but it's really interesting. I think like any language that you use, like if you take like a hard look at the data structures, like even ones you think like arrays, for example, you're going to find some really interesting stuff underneath the covers.
Might I point you to Float?
Yep, Float. And, JavaScript has objects, but they're basically like hash tables. So, that's something or also referred to as associative arrays. Do you guys see anything about associative arrays and how they differ or are the same? Is it just a synonym for hash?
I think they're a synonym because actually when I searched for just, if you go to associative array on wiki, so ian.wikipedia.org/wiki/associative_array, data or the dictionary type redirects there, associative container redirects there, map redirects there. So there's several other terms that are very much in line with what we're talking about, right? So an associative array / dictionary, basically the same thing.
Yep.
Yeah. Going back to the handbook for a moment, we've had all this conversation about arrays in JavaScript, right? And things like that. And it was actually saying like, okay, well, now that you know about this, actually arrays under the covers are just a dictionary in JavaScript.
Yeah. Sometimes.
Exactly.
Until it's not.
Yeah. But yeah, everything has an asterisk.
Like an associative array, which is a dictionary.
Right.
Yeah. So as for the pros, it's basically the same as the hash table, except in static languages, you can be a little bit more efficient because there's no boxing necessary. We did episode way back on boxing, episode 2. So operations are safer and the errors are caught at compile time. And perhaps, maybe, there are some performance gains to be had because presumably the size of the objects that you're storing as keys and also as values. So maybe there's something there, although I don't have an authoritative source on that. Cons are the same as the hash 2, and there's something about a class resolution strategy that I don't know about.
Who put that in there? Was that you, Outlaw?
The class resolution strategy? What?
Yeah,
I didn't.
Okay. That was some sort of.
Maybe that was supposed to be like different conflict or collision resolution strategies, and class got written. Instead?
I think maybe we had a collision on the Google Docs document, and we have a errant line posted here. It's moving right along.
Yes.
When to use it's basically the same as hash table. So whenever you need a hash-like data structure, but you want that type safety and you're working in a language that has it, you need those fast inserts, those fast deletes, fast lookups. And another case I mentioned there was like if you have sparse data, so you don't necessarily want to pre-allocate the whole universe of what you might use if you know you're only going to be using a small percentage. And this is a really memory and efficient data structure that's still going to give you fast random access.
Yeah, I mean, kind of going back to my summary of the hash table, though, like when to use the dictionary is like always, because
always, yeah.
You should prefer the dictionary over the hash table would be my opinion.
Yep.
At least in like a language like C#, for example.
And one thing I don't think we touched on earlier is that hashes and dictionaries don't generally support ordering. So if you add the keys Abigail, Alan, and Brad, and then you and Outlaw, don't want to leave you out, and then you say, okay, get me the keys, loop over, I might get Outlaw first, and then Brad, and then Abigail, and then Alan. There's no type of guarantee built into that data structure definition on what you're going to get returned. Now, some languages, like in particular C# has like ordered dictionaries and I ordered dictionary interface, in which case they basically end up storing some sort of list or array data structure that keeps those things in order that you sort them or that you insert them in, so they can return those to you. That's going to be a specialized form of this data structure, but I just wanted to call it out just to kind of highlight the fact that there are a lot of variants that you might find in different languages or for very specific purposes that are going to be similar to a hash table or a dictionary. They're going to be just a little bit different for whatever reason.
Yeah, so I have a summary here of like the dictionary versus the hash table as it relates to C#. And much like Joe already said, the dictionaries are strongly typed, whereas the hash tables aren't. So we've got an example of how you could get yourself into trouble with the hash table by mixing those types. And in hash table, it would be perfectly valid code. Well, it would compile, could work, but whether or not, the validity of it would be what you actually want, we could argue. But so the dictionaries in C# are much like the Java hash table, where you would have the key and value types, as generics.
Hey, I just had a thought. What if you were trying to truly just store a collection of random things? You didn't care strongly type. That's a good point. That's a good time that you might use the hash table over the dictionary.
Oh yeah, sure.
Right?
Yeah, that's a good point.
Kind of like in the last, maybe was it the last episode where I'd mentioned where you might have the array of pointers and each pointer pointed to something different.
Yeah, something like that. Exactly. Yeah. So a hash table might work there really well.
Yeah, an example I like there is like if you have an array and you want to get the unique items out of it. One strategy for doing that is to loop through that array and throw those items into a hash table. And whenever there's a collision, or rather you try to store the same key twice, then you might say, okay, this item's been duplicated, either kick it out or do something special with it. But in that case, all you really care about are the keys. So you're throwing this thing into a hash table or a dictionary, but the value is what? 0? Is it true? It doesn't matter because all you care about are the keys. So that's kind of an interesting case there.
Yep.
Here was another, just going back to this Java versus C#, the dictionary in C# versus the hash table in Java, both of them being typed. It was kind of curious that in Java, the hash table actually extends dictionary.
Well, it's hash map, right, in Java?
No, wait. I'm not talking about hash map. I'm talking about hash table.
Extends
if you look at the class, you want to get confusing now, right? Because our whole build up here is we've used hash table to build up to our understanding of what dictionary is, but in Java, hash table extends dictionary.
Oh yeah, I just tweeted at Larry Ellison. I said, "Yo, what gives Wikipedia says the dictionary comes after." The dictionary is strongly typed. So why are you gonna
coding blocks on that?
Yeah, that's right. Send your tweets to at Larry Ellison at.
Yeah, it's actually up on the Oracle docs, though. You're absolutely right. Java, now the dictionary extends object, and the hash table extends dictionary.
To your point, yes, you should in Java prefer hash map over hash table. And I forget why there was like some performance optimization that was made. I'm not enough in the Java world to be able to like speak to that with any kind of authority. But last point I wanted to add here, though, in this hash table versus dictionary kind of wrap up is that the JavaScript object we talked about already could be used like a dictionary. You can use it like an associative array.
Yep. And I do many, many times.
We all do. Yeah.
Especially for caching.
Yeah, all the time.
Would you consider that an abuse of JavaScript?
No, that's a good use of JavaScript.
Just what we did.
That's the appropriate use of JavaScript.
So last episode we talked. Last episode we talked about arrays and similars. I'm not going to be implementing my own array, but for linked lists, like I don't have a problem implementing my own version of a linked list over using like C#'s built-in one. Now that I know about the built-in one, I'll probably use it, but it doesn't bother me to think about somebody recreating a linked list or even a stack. Like you can really easily make your own stack. So if you don't use the built-in one, fine. In JavaScript, fine. Just use an array and push, pop, whatever. You've got a stack there, good enough. However, Hashtable is one that I will not be writing on my own because I want that really good distribution of those keys. And that's not something I'm confident in my abilities to do without spending a lot of time researching something that I'm really not interested in knowing that much about.
So yeah, we've got tons and tons of resources that we'll link to here in the show notes.
Mm-hmm.
I mean, we've got a lot.
Yep.
And with that, it is time for my favorite part of the show. It's the tip of the week.
All right, and I'll start us off. We have a Slack. We talk about all the time, and go to codingblocks.net/Slack, and you can send yourself an invite and hop on in there. It's a lot of fun.
That's right.
One thing I'll tell you though is because we have a lot of people, a lot of active conversations going on. We have our data truncated by Slack all the time. So you'll see a lot of channels that sometimes they're just empty, and so you might join an empty channel and think it's dead, but really it was really active 2 weeks ago, and it's just 3 days have gone by, and the Slack Langoliers have eaten it. So one of those channels that sometimes goes dormant. Yeah, you like that, Langoliers?
Yeah. Okay. Langoliers. I thought you mispronounce it or pronounce it some other way. I'm like, wait a minute, no, I thought it was pronounced Langoliers.
It's like I read it, I didn't watch it
this whole time.
Stephen King, he still hasn't answered my tweet. Anyway, so we have these channels that sometimes look dormant, but sometimes they wake up with a passion, and one of those is hashtag pet-pictures. It's lit right now. So Jacob started the fire. He posted a picture of his pupper laying on its back. Arlene sent oh my gosh, hold on, sorry. I started watching it. Arlene posted a picture of a cat fetching a fork, which is ridiculously cute as it sounds. Crittner had his cat on trampoline. Anyway, it just went on and on and on. So the real tip is you should join the Slack, and specifically you should join that Pet Pictures channel because it's lit right now. It's awesome. There's so many cute animals in there that I'm dying, but so far they're only cats and dogs. And I know you out there, dear listener, someone has a cute lizard or a squirrel or something, and I want to see it and think about petting it while I'm working, because we all need that positivity this time of year.
But wait, Logan posted a picture of a dog that looks very angry.
That was the best picture he could get of it. It's an all black dog. So he's talking about how I love this channel. He's talking about how it's hard to get a good picture of it. So
yeah. So
yeah. Look at the teeth on that dog.
Yeah. Fantastic.
How are you going to talk smack about the man's dog? Come on now.
I'm talking smack. It just looks really unhappy. You need to pet your dog, Logan. Pet your dog.
Oh boy. All right. Well, I'm gonna go warn them in the Pet Pictures channel about this episode coming out. Like, Logan, listen, your dog comes up.
All right.
I'm sorry to say.
I guess, am I next? Yeah, I'm next. All right. So I don't know how I've been on the interwebs as long as I have and been as interested in big data as I have. As a matter of fact, I got a question, or we all got a question. I think I'm the only person that responded that was, what are your current interests? We hear that you're C# guys or whatever. And so I posted some of my interests up there, and a lot of them revolve around this whole big data and just data in general, right? I'd never heard of Grafana. You guys?
A little bit, just because I was looking at the search talk I did a while back. That was a really good example of visualizations based on like time series type stuff. And so I know that it goes hand in hand with Prometheus. Is the only time I've ever really seen it used.
Yeah. So this thing it's awesome. It's an open source package that you can hook up to 51 different types of data sources. 51. That's like
nuts.
Yeah. And you can literally just build dashboards on the fly. So if you've got some time series data or something, you want to be able to visualize it, hook this thing up to, your Kafka or your Elasticsearch or whatever you want. Like he said, Prometheus, CloudWatch, probably any Azure alert type things. And you can actually drag a panel up there, drag a chart up there, hook it up, tell it what the columns are, and boom, you have this thing that you can go look at. And I believe it's even got alerts on it. I can't remember. But yeah, totally. This thing's really cool. And it looks like a really quick way to be able to start visualizing any kind of big data or even just data that you have access to. So check that one out.
Should we answer now about the things we're interested in, or why not?
I say you put the post up on the page. I don't remember where I put it, though. I don't remember which episode that was. But you can, yeah. I mean, you guys want to do it real quick? What you're interested in thing?
Is it fast?
Is it fast? How many tips? How many things you interested in?
Like Python, data science, JavaScript, machine learning.
Okay.
Like those kind of topics. I mean, topics we've talked about. They shouldn't shock you.
Yep. No.
DevOps.
Yep. What about you, Joe?
I don't understand the question. Is that what we're interested in?
Yeah, the types of things that you're currently like hot on learning about, or just.
Oh yeah. I know that. I
All
totally
right.
know that.
Well, tell us.
Oh, you guys can tell us.
No, hold on. I'm thinking. No, no, absolutely. I am very super interested in. I really want to focus in 2019 on two things: search engines, so Elasticsearch, Search, Algolia, stuff like that. I think you can build a lot of really cool user experiences with it, and the Jamstack, which we're going to be talking to you about really soon here. I'm really interested in Jamstack, and I'm worried about my little kind of middleware island shrinking year after year, and I'm deciding to join them rather than be beaten by them. So front end, all the things.
Really? Jamstack? I
Jamstack
swear
is
I thought you were just messing with me when you said that previously.
No, man. That's my profile on Dev too. Man, I've been changing everywhere.
The very first time he mentioned something about it, I assumed it was a reference to Dance to Die's article where he'd referred to Joe Allen Michael as Jam.
Jam.
Yeah, I don't think I ever saw part 2 of that article. Dance to Die hooks up.
Yeah. So you're totally on board with that. All right.
Yeah, Jamstack and Search.
All right, then.
Software for humans. That's me.
All right.
All right. So my tip of the week comes to us from Angry Zoot. Thank you, Angry Zoot. Is to add emojis to your file, or oh my God, if you use this in your code, in Visual Studio Code by using window plus the semicolon, and it'll bring up a little window that you could like select the emoji you want to use. So you could say var foobar equals, and then put a smiley face in it.
Oh, that's amazing.
Or worse, you could do var smiley face emoji equals foobar.
Oh, that's amazing.
In which case, I'm going to be like, why would you do this in your code? But you can do this in Visual Studio Code without any add-ons, without any extensions, plugins, whatnot.
Zoot, you're awesome.
Yeah.
Or all my variables.
Or maybe you're not, because if Alan starts using this to name his variables, I'm going to be looking at like, wait, smiley face plus frown face equals meh face?
Oh, that's amazing. Right? Smiley plus smiley equals super smiley? Oh, dude, this is going to be great.
If smiley greater than 0.
Yeah. I mean, really though, I am so on board with emojis everywhere, and it's Dance to Die is actually the reason he made those ticket templates for QIT, where it would say like steps to reproduce or environment, like that sort of thing. But he used emojis, and it really broke it up visually, and so you could kind of look at this what would otherwise be kind of a blob of text and see like, okay, there's 3 parts to this, and here's some visual indicators as to their meaning. And so now I see him everywhere. MVP Nicholas, he has his Advent of code up on GitHub, and he's got a couple stars there that represent the kinds of problems because you're rewarded with stars, and it just looks really nice. And so when you go to a page like GitHub that's so text heavy and you're so used to seeing it, and all of a sudden you see these cute little pictures that kind of like divide up the thing that you're looking into sensical operations, like suddenly emojis aren't so crazy.
That's really cool. I want to see where you're talking about. Where's the QIT one with the emojis? You have
just go create an issue. So if you go to github.com/codingblock/podcast-app and create a new issue, you'll see when you select the issue type that it gives you a template that asks you to fill in different things when you create the ticket.
I want to create a new issue.
Yeah, and Dance to Die, man, he is the emoji master for sure.
Oh man, it wants me to log in. What's that about?
You're not always logged into GitHub. Come on,
man.
Oh, I still got an open pull request there. Oops.
Dude. All right. Well, so very coolness. Thank you.
All right. Well, with that, hope you've enjoyed this episode of Hashtables versus Dictionaries. Be sure to subscribe to us in case if a friend happened to let you borrow their device to listen to this, or if they sent you a link and pointed you to the right place. But be sure to subscribe to us on iTunes to hear more using your favorite podcast app. You can leave us a review if you haven't already. Like Alan discussed earlier, you can head to www.codingblocks.net/review.
And happy holidays to all, right? What everybody doesn't know is Joe Zach, while he seems like he's probably the most festive of the bunch of us, he is the Grinch. of the three of us. So
Yeah, I am one of those warriors that you hear about that is actively trying to destroy Christmas. Sorry.
So truly kick him in the shins if you see him during this.
I legitimately hate holidays.
That's crazy talk. So anyways, happy holidays to everybody. And while you're up there at codyblocks.net, check out our show notes, examples, discussions, and more.
And send your feedback, questions, and rants to the Slack channel because it's brilliant and awesome. There's awesome people in there. And you can get an invite there by going to codingblocks.com/Slack.
Yeah, and Logan, pet your dog. Pet your dog.
And you can also follow us on Twitter or head over to codingblocks.net where you can find all our social links at the top of the page.
Love you guys. Thanks.